please submit today itself and mention the reason also. Okay.
Okay, sir. Thank you.
Yes. Okay. I think time is okay. Now almost we go to start now. 40, I think 47 and almost 55 is there. 55, 56 students is there now till now. Okay. So now today whether the screen is visible for you, please check. Yes.
Yes, sir.
Yes, sir.
Yes. Yes. Okay. So this is a lecture number 7. That is lecture number 4. Already we discussed, that is problem solving. And lecture 5 and 6 is the practical. So already we did the practical last week. So that is lecture 5 and 6. And today we go to see lecture 7. So this is the lecture 7. That is EK diagram and direct and indirect, both direct and indirect band gap semiconductors. So what is the meaning of direct band gap semiconductor? What is indirect band gap semiconductor? So how you go to differentiate this? So each and everyone you go to discuss today. First you go to see what is EK diagrams. EK diagram. So what is the term? So I think E already you know, that is energy. Okay. K, that is a momentum, or some way you say wave vector. Wave vector. Okay. So that is EK, energy versus wave vector, or energy versus momentum diagram. So that is EK diagram. So in the normal band diagram, for example, in the normal diagram, I think you see the diagram. I go to show the diagram here. One diagram. You please check whether the diagram is visible for you. Check. Yes. See, diagram
Yes,
is.
sir.
So this is a normal the energy band diagram. So here you see there are so many energy levels. For example, first energy level, second, third, fourth, and the valence energy level. That above the valence band, the conduction band is there. So this is the valence band and this is conduction band. I think you know valence band is partially filled. Conduction band is almost empty. Yes.
Sir, the PDF is not completely visible. The half of the screen is visible.
Wait. First you see the diagram, then I will move that side. Wait. So the diagram is visible for you or not? First.
Yes, sir, it's visible.
Yes. So the remaining thing I will take care. Just wait. See, this is the diagram. This is a normal diagram. Energy band diagram. So this is a valence band and this is a conduction band. In between. So what is that gap? So that is the energy gap. Fermi energy gap. So between these two. So this diagram, for example, I think now you go to come to move on to here. So that is a conventional band diagram. So the conventional band diagram, I think you show only the band gap details. You see only the band gap. Atul, mute your mics. All of you mute your mics, please. Yes. So that energy band diagram, conventional band diagram shows only the energy gap. So what is the energy gap between valence band and conduction band? But other details, for example, optical properties or mechanical properties or electrical properties of semiconducting materials is not exactly realized by using these type of diagrams. Okay, so how you go to know this is optical material, this is electrical properties and mechanical property, and there are so many dielectric properties on anything. So with the help of this diagram, it is not possible to understand. So that's why you go to take one more diagram, that is energy versus momentum diagram. That is EK diagram. See, the K is nothing but momentum and E is energy. So mathematically, the K is a wave vector. So that is the reason you say the K is wave vector also. EK. So energy versus wave vector diagram. That is EK diagram. EK diagram. So that EK diagram shows the characteristics of semiconducting materials, particular semiconducting materials. So if you go to see the EK diagram, very easy to say. So whether it is direct band or indirect band gap. So direct band gap means.
Sir, can you show the diagram once again?
Yes. Which diagram? This is a normal diagram. This is a normal band diagram. See, this is a normal band diagram. I think this diagram already you know in the 12th standard. Yes.
Yes, sir.
Yes. See, for example, valence band, conduction band, both are overlapping. So what is the type of conductor? You know, I think there are 3 classifications. That is a good conductor. If the difference, for example, the gap is order of some 1 electron volt or something, you say that is semiconductor. If the gap is too large, you say that is insulator. So this is the normal band diagram. With the help of this, which one you go to understand? Only that energy gap. So from this diagram, so I know only what is the energy gap between valence band and conduction band. There is no other details. Okay, are you understand? Yes.
Yes, sir.
So now, okay, that is the reason you go to take. How you go to draw the diagram first? So last class Okay, moving in the periodic potential. So in the periodic potential, how that energy band, how the electron they goes to behave, and based on that you draw some diagram also. So in the diagram you understand that is allowed energy band, then a forbidden gap, then allowed energy band, forbidden gap, like that. So you go to see one more diagram. I go to see the show the diagram here. See, so whether I think the diagram is visible for you? Yes.
Yes, sir.
Diagram? Yes. Okay. So now the diagrams are visible. Theoretical part I will show later. I will explain here. No problem. See, and this is the case where the particle, for example, most of the semiconducting materials are crystalline in nature. So what is the meaning of crystalline? What is a crystalline form? Anyone? There is a regular and periodic arrangement of atoms or not?
Yes, it is
Yes,
there in
sir.
system.
Yes, yes. So regular and periodic arrangement of atoms. So you say that is a crystalline form. The most of the metals and semiconductors definitely is a crystalline in nature. So therefore, definitely they have the regular and periodic arrangement of atoms. So like this, for example, see how the potential energy. For example, you go to see this is the energy along the x-axis. Sorry, y-axis. You see here, and this is a R with respect to the distance. I go to take it here. Okay. So now the potential energy, for example, I go to take only one electron, or for example, only one atom, you say hydrogen atom. So in the hydrogen atom, so what is the outermost electron? How many electrons in the orbital? Only one. Is it correct? So the atomic number is 1. So there is only one electron and only one proton. So in the orbit, in the K shell, only one electron is there. So maybe, for example, how the potential energy is varied here. So simply you go to see this diagram here with respect to R. This is the variation of potential energy like this. So coming, okay, that decreases and reaches the value, minimum value, and goes to maximum. Again comes to minimum and reaches the value, minimum value. Again it go to maximum like this. See here. So comes to minimum and reaches the maximum value again. So like this. So this is for one electron system, that is okay. But our case is metals or semiconductors. So for example, you say this is a semiconductor physics. You go to see semiconductor. So definitely that is n number of atoms, not only, for example, outermost orbital only one electron. A number of valence electrons are there. For example, if you say silicon, germanium, the outermost orbital there are 4 valence electrons are available, I think. Okay, last class we discussed. Is it correct? Yes. So silicon, the 3s2, 3p2. I think you were discussing that how the band formation more. Are you remember?
Yes, sir.
Yes. Okay, so in that cases, for example, n number of atoms are there. This is single case, okay. For example, n number of atoms are arranged like this. N number of atoms. So see, this is a periodic, regular and periodic arrangement of atoms like this here. This is a regular and periodic arrangement of atoms, and this is the dotted lines indicates how the potential energy varied with respect to the each and every atom like this. See here, at each and every one. Similarly, in the second case, for example, I go to draw the diagram, the Vx, that is potential energy versus distance. With respect to distance, how it goes to vary. So the potential energy also varied periodically. Are you understand? Yes. See, this is V of x. Okay, this is in the arrangement of atoms. That is a regular and periodic arrangement of atoms here. So how the potential energy is varied? See here, starting from 0 and comes to minimum, again goes to maximum here, again comes to minimum. So like that. So this is periodically changes. See, in between x is equal to 0, in between 0 to a, in between a to 2a, and 2a to 3, etc. up to the final. For example, the width of the barrier, for example, I go to take L. So in between 0 to L, how the potential energy is different. That is a periodically changes. See here, periodically changes. So whether are you understand this or not, please. Yes?
Yes, sir.
Yes. Sir. So the potential energy is also periodically. Such way the block introduced that term, that is I k of x is equal to e power I k of x into u k of x. So here the periodically changes. That's the n number of atoms are arranged to form the crystal. Then there is overlapping. Definitely individual atom they get overlap. So due to this, the potential energy of the electron inside the crystal is varied periodically. So that's why you see the crystal is periodic. I think now you come to the theoretical part I show here. I already explained all these things. See, for example, one electron system, that is very easy to solve the Schrodinger equation. If more than For example, a number of electrons are there. In the case of solids and semiconductors, large number of atoms are there, and a number of electrons also present. So how you go to solve that Schrodinger equation? This case, because according to Bloch, the potential energy is moving. It also depends upon the position of the lattice inside the crystal lattice, and Bloch assumed that the probability of finding the electron is also periodic, and the wave function associated with this electron is also periodic. I understand this because each and every one is periodic here. Okay. Yes. Yes. So each and every one, that is a periodic. That's why how you go to solve the equation. So simply I go to take the probability of wave function, that is modulus of psi whole square. That is the reason. See here, the probability of finding the electrons is equal to, that is a say normalization. So that is modulus of psi whole square. That is psi star. You say psi star. I think it's not read to you, but just you know. So how you go to find out the probability of finding the electron? That is modulus of psi whole square. In a one dimension box, it is coming. So how you go to take this one? That is modulus of psi star or modulus of psi whole square. So now once you go to solve this equation, that is Schrodinger equation, and then you get that energy value. Based on that, you go to draw the diagram. That is EK diagrams, the energy versus K. So how you go to solve the diagram, Schrodinger equation? There are too many cases here. See, for example, last class we discussed that the KP model take into account that Bloch, that UK of x, e power ik of x into UK of x, because Bloch introduced that wave function. So now again the same I go to take it here from the Schrodinger equation. See, this general time independent Schrodinger equation, that d square psi by dx square. See, last time you studied that is 8 pi square m. So both are same. That h cross is equal to h by 2 pi. Please understand that h cross square here, that h cross square is there. So that is nothing but h by 2 pi. Okay, the 2 pi square goes to numerator, that is 4 pi square. Already 2 is there. So that is 8 pi square m by h square. Are you understand this? Yes? Say yes or no more, whether are you understand or not? Yes? Anyone?
Yes, sir.
So that is 8 pi square m by h square, or that is 2 m by h cross, both are equal. So that's what I'm telling. D square psi by dx square plus the 2 m by h cross, that u minus psi is equal. This is a one dimension time independent Schrodinger equation. Now according to that Bloch, that the potential energy V inside is a periodic, because now only you say the V is inside the crystal is periodic. So now you go to write that is V of x. So V of x, then up to A, that is a dimension. For example, the in between A there is 2A, 3A, 4A, 5A, etc. up to L. So now instead of writing V of x, I go to write V of x is equal to V of x plus A. So I'm taking both. Again, the periodic potential can be written by means of lattice constant, that is A, that is a lattice constant A, that is V of x plus A. V of x plus A. Now come to the equation. According to that Bloch equation, that is UK of x is equal to e power that ik of x into UK of x. This is the Bloch function. So instead of here x, I go to take x plus A, e power ik x, that is UK of x. So instead of UK of x, where UK of x is equal to UK of x plus A, so because this is due to periodicity of the crystal, that is periodicity. Now again you go to substitute. Instead of psi, I go to take, instead of psi, already in the KP model already we discussed, you replace that d square psi by dx square by in terms of u, that is UK of x, Bloch's equation. Then finally you go to solve the equation, and finally you get the graph. I think you remember. So last week you draw the graph between alpha A versus that p sin alpha A by sin alpha A plus cos alpha A. The diagram already you see in the last class. Okay, that time I told. So that is the energy bands. So how the allowed energy bands is there, then forbidden gap, allowed energy bands like that. So from this equation, you go to solve the Schrodinger equation again, that d square psi by dx square plus 2m by h cross square e minus v of x. Now instead of v, see here equation 1, that is v. So now that is v of x, that is v of x plus a. Similarly uk of x, that is equal to 0. So now you go to solve this equation. Okay, so after solving this equation, you plot the graph between the eigenvalue of energy, that is eigen energy values, versus wave vector, that is a k, wave vector k. So you get the EK diagram. You get the EK diagram. And you understand? Yes.
Yes, sir.
Yes. Okay. Now you go to see how many types of EK diagrams are available. So there are three types of EK diagrams are there. So now I go to explain one by one. See, first you know how you go to draw the diagram. So there are three types of diagrams. So please remember. See this. First I go to show the diagram. Please understand the diagram. Then I go to explain one by one. Okay. Whether the diagram is visible, please check. Diagram is visible or not? Yes.
Yes, sir.
Yes. Okay. See, this is the middle portion. For example, I go to take. You don't draw the lines now. First, you draw the waves. Okay, wave pattern. See, for example, I go to starting from here. See, starting from minimum and reaches the maximum, comes to minimum, again goes to maximum. So like that, you can draw the sinusoidal line. See here, this is a curve here. Okay, just above. Again, you go to draw the same, but one difference. Only one difference. That is, this is coming from where? Minimum. See here, this is coming from minimum. They go to reach its maximum. Again comes to minimum. Again they go to reach the maximum. Now what is the second one? Starting from maximum. See here, maximum comes to minimum. Again goes to maximum, minimum, maximum, like this. I understand this. Yes. Say yes or no. Say yes or no.
Yes, sir.
See the first one, the normal. See, this is a normal sinusoidal curve waves. So initially I go to first one. I go, for example, I go to see all the odd numbers. That 1, 3, 5, so etc. You go to draw like this. That is starting from minimum and reaches maximum, comes to minimum, like that. Then all the even number. For example, I go to take this is 2 and this is 4, like that. Starting from maximum here and then comes to minimum. Again goes to maximum, like this. So once you draw the diagram like this, then you go to select, for example, center part. I go to select the center part and I go to draw the line. Okay, this is E versus K. For example, this is a wave vector K. So the wave vector is changes, periodically changes both sides. Okay, my positive x direction, negative x direction. So that is pi by a is there. So that is n pi by a. Simply that is n pi by a. Okay, so k is equal to n pi by a. I think you remember that KP model. Yes. See the condition more that sin ka is equal to n pi or k is equal to n pi by a. Okay. So that is a condition in the KP model. You see sin ka is equal to n pi. That is a condition, or that ka is equal to n pi by a. So that n pi by a, I go to take n is equal to 1, 2, 3, 4, 5, 6. For example, I go to take n is equal to 1. That is pi by a, my right hand side. So the left hand side, that is minus pi by a. That is not mentioned in the diagram. So simply they are mentioned here the even numbers, 2 pi by a, 4 pi by a. But in between, odd number is also there. That is pi by a. Here is 3 pi by a. Minus pi by a, minus 2 pi by a, here minus 3 pi by a, like that. See, and this is a E, that is a energy versus K, that is a wave vector diagram. This is a wave vector diagram. And so this region, you see the region here, this is E versus K, and this is a normal case. You go to the normal case. So that is a periodic. Okay. So now, what are the different type of, say here, first in the periodic zone. In the periodic zone, so that is only the allowed energy values. So allowed energy values in between. For example, I go to take that K vector, in between minus pi by a is less than K, and that is less than pi by a. So that is also the entire K space, the gap. Okay, the periodic repetitions of allowed energy bands are allowed values corresponding to the each allowed band, and which is obtained by the periodic repetitions of the region where that minus pi by a less than K, and that is minus pi plus pi by a. That is one region. Similarly, the minus 2 pi by a is less than K, that is 2 pi by a. If you put n is equal to 1, 2, 3, 4, like this. Okay, and this type of diagram you go to say that is a periodic zone diagram, periodic zone. So here, see here the wave pattern you go to see that is periodically changes, potential energy periodically changes. Whether are you understand this one? Yes, students, whether are you understand or not?
Yes, sir. Yes, sir.
Yes. Next, extended zone. So that is again one more diagram. You see that is extended diagram. This is the second one. Here also same, but there is a discontinuity is there. See, in the extended node diagram, it is also in the this different bands. different bands are allowed. So different bands. It's not a same allowed energy bands. Here the different bands are allowed. See the diagram first. I go to show the diagram first. See here. So this is a 0, a middle mode, that is E versus K. So here also same, minus pi by A, 2 pi by A, 3 pi by A, 4 pi by A is there. My left hand side, first one is this minus pi by A, minus 2 pi by A, minus 3 pi by A, like this. See, in between 0 to A, pi by A. So for example, I go to take this variation of, that is variation of this energy variation. And this is a second case. But in between the gap is there. See, there is a discontinuity is there. That is not a continuous wave function. So there is a discontinuity in between that the pi by A and 2 pi by A. I think I will explain why that is happened in the next class. That is a Brillouin-Jones. You say that is a Brillouin-Jones, that in between, for example, the different zones are there. So that is the reason you say this is a extended. So that is extended zone diagram, and the discontinuous occurs where K is equal to plus or minus A. N can take values plus or minus 1, 2, 3, etc. So first one, minus pi by A to plus pi by A, that is the, you say that is the first Brillouin zone. That I explain in the next class with the help of the diagram. So how you go to select that the first Brillouin zone and the second, third, like that. Similarly, minus pi by A to minus 2 pi by A, and similarly plus pi by A to again the plus 2 pi by A. So that gap, you say that is second Brillouin zone, third, fourth, fifth, like that. So this type of Brillouin zones also you go to draw based on this extended zone diagram. So this discontinuity is where is due to the Bragg's law of reflection. I think you go to see the law of reflection, like that. Then edges where the allowed band is K, that is equal to N pi by A. And the third one is, last one is reduced zone. So that is only one more in between one, that is pi by A to minus pi by A, or like that. So that is, you say the reduced zone diagram. So in the scheme, the first Brillouin zone, for example, you go to see the first Brillouin zone. The first zone is nothing but minus pi by A to plus pi by A. See here, that minus pi by A to plus pi by A, that is the first Brillouin zone. So that you say that is a reduced zone diagram, reduced zone. So the scheme is first Brillouin zone, since that EK diagram is periodic in between that first Brillouin zone, and it is sufficient to restrict the first zone itself. So that's, you say that is a reduced zone diagram. See here, up to this, plus pi by A to minus pi by A. Are you understand? So now I go to remove all the other terms. Simply I go to erase everything. I go to select only minus pi by A to plus pi by A. Yes? So yes or no?
Yes, sir.
So this is the reduced zone diagram. This is the reduced zone. In the reduced zone, so you consider only the first Brillouin zone. That means what is the meaning? So that is in between minus pi by A to plus pi by A. That's all. Okay. If you know the energy value of this first zone with respect to the wave vector K, and we know the everywhere because of the eigenvalues are periodic, and very easy to say the properties, mechanical properties or optical property or electrical property, like that. Okay. So most of the books, I think the textbook, they go to show the periodic zone, the reduced zone, like this. So now in from this zone only you go to the next class. For example, the next topic, you see the direct and indirect band gap semiconductor. So now you go to take this type of reduced zone only. I think the one more diagram, the next slide, I go to show the one more slide. So that is a reduced zone diagram for the semiconductor. See here. So this is a EK diagram. I think the top electronics books they are giving here. So this is minus pi by A, so plus pi by A. So this is a EK diagram for the reduced zone. That is only one zone, minus pi by A to plus pi by A. That is the first Brillouin zone here. So valence band is there, conduction band is there. How the energy can be emitted. See, this is the energy gap. Okay. So this is the energy gap here. This is EG, valence band, conduction band. You go to see the sides, the conduction band and valence band partially filled. Conduction band is also, the see here the electrons are there, and this is holes. How the energies are coming. For example, the electrons coming from conduction band to valence band, that is recombination takes place. The energy is released with respect to the energy difference between these two. So that is a photon of Hg is coming out. Okay. So this is the reduced zone diagram, EK diagram, or direct band gap. So I am telling how you go to say this is direct band gap and indirect band gap. You go to say next, that is your next topic. So what is a direct band gap semiconductor and what is the indirect band gap semiconductor, like that. Okay, are you understand this? Yes. So this is a reduced zone diagram. that is minus pi by a to plus pi by a for first Brillouin zone, for the first Brillouin zone. Yes? Say yes or no more, then only move on to the next one.
Yes, sir.
Yes? Okay, come to the next. So now, first I go to show some diagrams. You see the difference, then only I go to explain one by one. Okay. So first I go to see the diagram. Okay. So what is the difference here, the diagram? So what do you go to understand from these two diagrams? Anyone? Anyone come forward and say, what do you go to understand here from these diagrams? Yes? Anyone? So this is a reduced zone diagram. For example, I go to take this a reduced zone diagram, EK diagram. There are two different diagrams are there. This is a valence band, conduction band. Here also valence band, conduction band. So what is the difference here? What is the difference? Anyone? Yes? Or what do you go to understand from the diagram? See, say yes or no, yeah. Then only whether see, you see any difference between these two diagrams or not? Say yes or no. Is there any difference between the two diagrams?
Yes, sir.
Both are same.
Yes. Yes.
Okay, difference. Okay, where is the difference? Where you go to observe the difference here?
The upper parabola part has been shifted.
Yes. Okay. I think now you understand. That is the reason I'm telling. You first carefully go to observe the diagram and see where is the difference. So based on that only you go to differentiate. There are two type of semiconductor. That is a direct band gap semiconductor and indirect band gap semiconductor. Okay. So now you come to the theoretical part. See here. So first, for example, what is the significance of these EK diagrams? That's what I'm telling. So now we discuss the EK diagrams. Already I told by using the normal conventional diagram, it gives only the energy gap. That's the value of energy gap. But what about the EK diagrams? By using this EK diagram, so definitely go to identify not only the E gap. Definitely E gap is also identified. But apart from this, you go to see the demonstrate the electrons mobility and similarly explain the holes mobility and effective mass. And this EK diagram indicates how the electron states are different from other states. For example, electron equally spaced in the space and clearly shows the direct and indirect band gap semiconductor. So all these things you go to observe with the help of that EK diagrams, by the EK diagram. Definitely asking what is the physical significance of EK diagram. In 4 mark questions, at least you go to write any 4 points here. So the normal conventional energy band diagram gives only the energy gap value, but the EK diagram, apart from the energy gap, see this indicates the band gap which is different between the top of the valence band and the bottom of the conduction band. Not only that one, and it demonstrates the electrons mobility and similarly the effective mass. I think at the end of this unit you see what is the effective mass. So that is also you go to explain with the help of EK diagram, and this EK diagram indicates how the electron states are equally spaced in the that EK space, then the EK space, K space, and clearly explain the direct and indirect band gap semiconductors. So these are all the significance of the EK diagrams. Yes?
Yes, sir.
Understand? Yes, because the question definitely will come. Okay, what is the difference between the conventional and that why you go to study the EK diagrams? So these are the points. Then come to the next topic, direct band gap, indirect. So already that diagram, already I show the diagram and you see the difference, where the difference is coming. So now you please understand that EK relationship is more complicated, and here the energy, for example, the relationship, the energy band formation depends upon the orientation of the electrons and the wave vector of the crystallographic axis. Not all the semiconductors or metals behaves like same, because each one having the different energy gap and they behaves different. That's why this EK relationship and the energy formation depends on the orientation of these electrons and the wave vector, electrons wave vector to the crystallographic axis. Now you go to see the germanium, silicon, the gallium arsenide, and so many cases, and you see the differentiate. What is the difference? The direct band gap and the indirect band gap like that. How you go to differentiate this? That is very, very important. How you go to differentiate the direct and indirect band gap? See the first diagram. See here in the first diagram, I go to explain. So this is the valence band. For example, this is a valence band energy level, and this is the conduction band energy level. So the maximum energy levels. For example, see here the maximum of that valence band. So exactly aligned with the minimum of conduction band. Are you understand this? Yes.
Yes.
Yes. So the maximum of the valence band. So this is the maximum of the valence band. Okay. And this is the minimum of the conduction band. Minimum. So both are exactly aligned in the same the straight line. You say that is a direct band gap semiconductor. So best example for this is gallium arsenide. So gallium arsenide is a direct band gap semiconductor. So here this is the maximum, the energy value of where valence band, and this is the maximum, the energy of conduction band, minimum energy. So both are aligned. Both are aligned. You say that is a direct band gap semiconductor. So in the case, for example, that's why I'm telling that is a example is gallium arsenide. The maximum of the valence band occurs the same value of K as the minimum of conduction band. So this is a direct band gap semiconductor, the example. Then what is the second diagram?
Sir, I have a doubt.
Yes,
Sir, gallium is not a semiconductor, sir.
gallium arsenide. See that?
Okay.
That is not gallium. After doping, gallium arsenide is acting as a semiconductor, not gallium. Yes.
Okay. Sir.
Yes. Yeah. See, next, okay, what is it? Come to the second diagram. The second diagram. So this is the maximum of energy levels of valence band, but the minimum is just shifted, not in the same K space, Are you understand what I am telling? Yes. See, here both are in the same K, but what about here? Slightly shifted. So this is indirect band gap semiconductor. So that is indirect band gap. See, indirect band gap. Oh, that indirect band gap, I think you know the normal germanium and silicon. Whether you know whether it is a direct band gap or indirect band gap. Any idea? I think it doesn't know that germanium silicon is a direct band gap or indirect band gap.
Direct band.
Direct. No, that is indirect band gap semiconductor. You see here. See, and come. So what is the advantages? So why that is a direct band gap and what is the advantages? What about indirect? I go to explain here also. See, for example, the direct band gap. See, this is the conduction band. This is the valence band. So definitely the electrons in the conduction band. Once the recombination takes place, so definitely the electron hole decombination takes place here. So the electrons are coming from conduction band to valence band and combined with holes. Definitely they are going to emit the energy of photon h nu. So that is exactly equal to the difference between the conduction band and the valence band energy level. But for the direct band gaps, in case of indirect band gap, so definitely that is not equal to the energy difference between these two. Are you understand this? Yes. Say yes or no, because this is a very important one. See, the direct band gap semiconductor, the energy difference between the valence band conduction band energy is exactly equal to the photon of energy h nu. But indirect band gap, that is not exactly equal because both are not in the same space. So here the alignment is different. See here, this is slightly shifted. So that is the reason you say that is indirect band gap semiconductor. So that is a definition. See here. Now you see the indirect band gap semiconductor in few semiconductors. For example, you say like silicon, the maximum of the valence band does not coincide or does not align with the same value of K minimum. You say that is indirect band gap semiconductor. That is indirect band gap. And the direct band gap semiconductor, the direction of the motion of electrons. For example, the direction of motion of electrons during a transition across the gap is unchanged, and similarly the energy difference is exactly equal. See, in the direct band gap semiconductor, the direction of motion and the efficiency is more for the transition between the electron hole recombination. The efficiency is more for a direct band gap semiconductor, and that is less for indirect band gap because both are shifted. That energy levels both are shifted. Here both are aligned in the same, so very easy to transition takes place. But here they like this, so it is difficult to make the transition here. Are you understand? Yes.
Yes, sir.
Yes. Okay. So that is the major difference between the direct band gap and indirect band. Anyway, that difference table is there. You go to see how you go to differentiate this. See here. See. Now you go to see here. This is a direct gap. This is a direct band gap. So valence band, and this is the conduction band. The photon of emission is coming out. So what's the? This is electrons and this is holes. So once the electrons hole recombination takes place, so definitely photon of energy is Hd is coming out. But this is indirect band gap. See here, the indirect band gap, the transition is like this, not a direct transition. The transition is like this. So that time, so definitely the energy difference is not exactly equal. That's what I'm telling here. So in the direct band gap or direct recombination occurs with the release of energy equals to the energy difference between where the Eg exactly equal to the level such as Eg. But in the case of indirect band gap, it's not exactly equal. That's why I'm telling the probability of radiative recombination is high for where a direct band gap semiconductor. Hence, the direct band gap semiconductors are used in the optical sources. Are you understand now? So why they are choosing the gallium arsenide? Because that is a direct band gap semiconductor. And next, see here, indirect band gap. Due to the relative difference in momentum, that K, the momentum is conserved by release of some energy to align the both the maximum minimum, and then the recombination takes place. So that's why here that difference, energy difference, is not exactly equal to Eg, and the probability of this radiative recombination is comparatively low compared to the direct band gap semiconductor. So therefore, the indirect band gap semiconductor, and the transition probability is less compared to direct band gap semiconductor. Yes? Are you understand?
Yes, sir.
Understand or not?
Yes, sir. Yes, sir.
Yes. Yes. So now you go to see the difference. Now I think the difference tabular column is given. So very easy to understand the difference. Say for example, you see here in the direct band gap semiconductor, very simple. Already I explained the maximum energy value of valence band exactly aligned. For example, you keep the light like this. So this is the maximum value of valence band, and this is the minimum of conduction band. So both are exactly aligned in the same K values. That's why they are mentioned. So aligned with the minimum energy levels of conduction band with respect to the momentum, that is K wave vector. But in the case of indirect band gap, so that is not aligned, exactly aligned. See here in the indirect band gap semiconductor, the maximum energy of valence band are misaligned with the minimum energy of the conduction band with respect to the momentum. And one more, in the direct band gap semiconductor, already told the recombination takes place. That's what I'm telling. The recombination takes place. The release of energy is exactly equal to the energy difference between valence band and conduction band. That is Eg. It's nothing but Eg equal to the energy difference. But in the case of here, indirect band gap semiconductor, that is not exactly equal. See, the first the momenta align themselves, and then the recombination takes place. That's all. This is the second. And efficiency, direct band gap, the recombination efficiency is far greater. That's why the efficiency factor is higher. In indirect band gap semiconductor, that is very less. The reason, both are misaligned. And example, the best example, that is gallium arsenide. For direct band gap semiconductor, the gallium arsenide is the example. That indirect band gap semiconductor, you choose silicon and germanium. I think already you studied in the lower classes that the silicon germanium, that is indirect band gap semiconductor. And direct band gap semiconductor always preferred over indirect band gap because they are a very good application for optical resources. All optical switching or optoelectronic devices applications, direct band gap semiconductor materials are used. Most probably the gallium arsenide, most probably they are used. That indirect band gap semiconductor is not exactly or not using because they are misaligned. That is the reason they are not used for optical sources. So these are the major difference between the direct and indirect band gap. Similarly, the probability, already I told, the probability of recombination is very high in direct band gap. So that is very low, comparatively very low for indirect band gap semiconductor. Again, the diagram they are given. So with respect to the diagram only, you say why that is direct band gap, and why you say that is indirect band gap. So this is the EK diagram, E energy versus K diagram, momentum diagram. So in that diagram only you understand why you say that is E direct and why you say that is indirect like that. So this is one of the significance of the EK diagrams. Are you understand this? Say yes or no more. Say yes or
Yes,
no.
sir.
I think now you understand clearly what is direct band gap and indirect band gap. Yes.
Yes, sir.
Yes. So from the diagram itself, you clearly understand. So direct band gap means both are aligned in the same K value. That is maximum of valence, minimum of conduction band aligned in the same K value. That is direct. For example, in the case of indirect, the maximum of valence and minimum of conduction band aligned, misaligned with respect to the momentum. So here you say with respect to the momentum K. So that is EK diagrams, EK diagram. So energy is also shifted here, there's no doubt. But with respect to momentum, along the x-axis, with respect to momentum, both are misaligned. So that is the reason you say that is indirect band gap. Any doubts or clarifications here, please? Any doubts or clarifications? Yes? Anything else here? Any doubts or anything else or any clarifications, please?
No, sir.
Yes? No doubts.
No, sir.
So whether I understand today's lecture, that is EK diagram. Okay, first it takes one small that's a revision now. So the normal conventional, that is energy band, doesn't give anything details other than energy gap between the two valence, that valence band and conduction band. But so how you go to take that EK diagram? So after solving that solving the equation with respect to the block condition, that periodicity in the crystal or inside the crystal, and the potential energy is also periodic. Therefore, the electrons movement is also periodic. And you go to solving the equations also, you go to take into account of the periodic. So that is the reason you have to take that the V of x is equal to x plus a, and similarly UK of x is x plus a. So once you go to solve that equation only, then only you get that eigenvalues. So after getting the eigenvalue, you go to draw the diagram versus the energy eigenvalue versus wave vector k. So you get the EK diagrams. There are three type of diagrams. One is periodic zone, extended and reduced. So periodic is nothing but you go to draw the allowed energy bands only. In the allowed energy bands, you go to draw the diagram in between the spaces minus pi by a to plus pi by a or minus 2 like that. In the extended zone, so okay, the different energy bands are allowed and the discontinuity is also there. The condition is that the k is plus or minus n pi by a. So you take minus 1 by 2 plus 1 by 2, okay, minus 2 by 1 by 2 and plus 3 1 by 2 like that. So there are so many variations. So n pi by a plus or minus, n can take 1 2 3 4 like that. And third reduced zone, that is only first zone, first, that is minus pi by a to plus pi a, that is reduced zone. So that is you say first Brillouin zones. In the reduced zone, the condition is you go to take up to minus pi by a to plus pi by a. So the details enough to say all the properties of the particular semiconducting material. For example, you see this is the reduced zone diagram. So in the reduced zone diagram, I directly go to see whether it is a direct band gap or indirect band gap. So whether it is using for optical application. So what is the probability of recombination? So all these things I go to say with respect to this diagram. So that is a reduced zone diagram. Then you see the discuss what is the significance of the EK diagrams. Then what is the two difference? How you go to define direct and the indirect band gap semiconductors. I think these are the things already you discussed in today's class. Whether you have any doubts or anything else, please. Any doubts or anything?
No, sir.
Okay. Okay. If there is no doubts, so simply I go to stop the share screen and I go to take the attendance. So please all of you give attendance.
Okay.
Yes. Tell me. Okay, I think out of see there are 77 students are there, but why only some 60 are I don't know why.
Sir, they don't know class timings.
Hey, class timings more than 2 weeks before already informed.
Sir, there is always confusion for this class. On
Yesterday,
on the
no,
student portal, it shows 1
yesterday,
p.m.
yesterday also I sent in Google Classroom whether almost all of you in the WhatsApp group or not.
Yes, sir. From there we know.
See, the yesterday itself I sent that the WhatsApp group also. Then what can I do? Okay, Nikhil, I think, yeah, I informed yesterday through GCR, through WhatsApp group. Still they are doing like this, means what can I do? Yes? Huh? Okay, anyway, we go to market absent. That is the only solution. Yes. So what about 51?
Present.
Okay, 52,
Present, sir.
53,
Present, sir.
54, 54. 54 is not there. Okay. 55.
Present, sir.
Yes. 56. Ashawadan present. Okay. 57.
Present, sir.
58.
Present, sir.
59.
Present, sir.
60. 60. Janavi. It's not there. Okay. 61.
Present, sir.
62.
Present, sir.
63. 63. 64.
Present, sir.
65. 65. It's not there. 66.
Present, sir.
68.
Present, sir.
69.
Present, sir.
70.
Present, sir.
71.